So we're going to be talking today about linear relationships. Linear relationships mathematically follow this formula: y equals mx plus b. Now, I know this is review for a lot of people. We are going to be focusing on this guy here. M stands for the slope. So that's what we're going to be focusing on here. The slope tells us how our two variables are related. So in the first example, I'm going to compare the study time on a quiz to a quiz score. Here's all the raw data. Hard to really see anything there, but if I click on this graph here, I've plotted all that data here, and I end up with what looks like a nice straight line. I can confirm that using the computer here to give me the trend line. And if I come down here and I click on the trend line, I do end up with a nice straight line. The thing that I want to point out here is if your straight line is bent upwards like this from the origin, so we're going in this direction, we would call this something that has a positive slope, or we would say it is a positive linear relationship. Okay, and again, slope, if you forget, slope is equal to the rise over the run. So if I were to draw a straight line here, there might be my rise, and then I go over here, that would be my run, and then I can calculate what the slope is. I'm sure you've done that in your math classes. This is just review today. So that's our first one, positive slope. The second one I want to look at here is So this is, we can go up to the data here, distance driven versus the amount of gas in your tank. And if I look at the data or the graph for this one here, I end up with something that looks like this. I can put in the trend line here so we can get an idea of what it looks like here. And when I put this one in here, I end up with what's called a negative linear relationship. Because in this case here, if I do the rise over the run, the rise is actually decreasing, becoming negative, and going over this way would be the run. So this would be an example of a negative slope or a negative linear relationship. Okay. So we have one other one that I want to look at here. And the last one is this one. Here we're talking about the number of baseball used at a baseball game, comparing that to the number of hot dogs that were eaten during the game. And when I look at this one here, this is the graph I end up with. I'll ask the computer to help me out again and put in the trend line for this one. And when I click on this here, I end up with a nice horizontal line. So that's a big thing to keep in mind here. What is this now telling me? This is not only good for physics, but also for your ACT work. Here it's saying that as the number of hot dogs consumed increases, the number of baseball used per game doesn't change. So in this particular case, we would say that there is no relationship. So there's no relationship between the number of hot dogs that are eaten in a baseball game to the number of baseballs that are used. So in this case here, the slope in this case is 0. There is no rise over run in this case. So that's one thing to keep in mind, okay? So the important things to keep in mind for this one again is, if I can get this back, we'll see if I can. So we've got our example of a negative slope here and we've got our example of a positive slope here, and we've got an example of no relationship whatsoever. So a positive linear relationship, a negative linear relationship, and no relationship.
So Mr. Willauer took us through the different graphing relationships, and before we move on to position versus time graphs, I want to quickly recap them because they're really important. So we had 3 different graphing relationships. So for any arbitrary axes, for our y-axis and our x-axis, our first relationship looks something like this. And we call that the positive linear relationship, all because it has that positive slope. Okay? Our second relationship for a y and x axis, again, it could be any variables there. It looks something like that, which we call that the negative linear relationship because it has a negative slope. Then for our third relationship, again, for any two variables that we are comparing, our relationship looks like this, which we call that the no relationship because it has a zero slope. There's no slope, there's no rise over run. So we're going to take a look at what will these graphs, these three graphs, mean if we look at them as position versus time graphs. So a position versus time, remember y versus x, a position versus time graph would look something like this, where position is on the y-axis and time is on the x-axis, which I know is kind of weird because position has that variable x and time has a variable t, so it's weird to have x on the y-axis, but remember x just stands for position. It's our symbol for position, so we're just putting position on the y-axis because it's our dependent variable. So we're going to take a look at what do those relationships mean as we put them in position versus time graphs. So the reason why I drew the axes like that and not like your typical graph is because we can't have negative time. We're always moving forwards in time. So we can't really have that whole left side of the graph. So I just draw my axes like that instead. So that's why I'm drawing it like that. We always think about the positives, not the negatives. So for our first relationship, let's say we've got a position versus time graph. Again, position goes on the y-axis and time is on the x-axis. So for our positive linear relationship, what is this telling us in terms of position versus time? So first thing we always want to look at is where does the object start? So at time is equal to 0, our object, whatever it is, it's at the origin, right? It's at position is equal to 0 as well. It's right there. At time is 0, position is 0, so the object starts at the origin. But as time increases, the position also increases. So that tells us that the object is moving away from the origin as time goes on. So it's moving away from its starting point. It's moving away from the origin, and it's doing that at a constant positive rate. Okay, we've got that positive slope there. So it's moving away from the origin or its starting point at a constant positive rate, constant positive slope. Okay, again, we're going to put some more context to this later. But that's our positive linear relationship in terms of a position versus time graph. The object starts at the origin and it moves away. So for a negative linear relationship, right, something that looks like that, again, we have position on our y-axis and time on our x-axis. Now, considering when time is equal to 0, so where is our object starting? Well, when the time or when the clock starts, when time is equal to 0, our object is not at the origin. It's at some positive position. So that tells us that the object starts away from the origin. It starts away from our reference point because our origin is just that x-axis line. Okay, that's our origin point. So the object starts away from the origin, but as time goes on, as time increases, our position decreases. So instead of moving away from the origin, like we saw before, the object it has that negative slope, so it's moving actually backwards. It's moving back towards the origin as opposed to moving away from it. With our positive slope, our negative slope tells you that the object is moving backwards, and it's moving back towards the origin, actually. It's coming back towards the origin, towards the reference point. It's doing that at a negative constant slope. Okay, so that negative slope tells us it's moving backwards as opposed to moving forwards away from the origin. It's moving backwards towards the origin. Okay, last one, and then we'll put some context to these. So with our no relationship graph, right, looks like that for position on the y-axis and time on the x-axis. Again, we always want to consider where is the object starting? Where is it located at time is equal to 0, when somebody starts the clock, okay? So here, again, it's not starting at the origin, it's starting at some positive point away from the origin. So the object starts at some point away from the origin, and as time increases, you'll notice that the position doesn't change. It stays right there. So the object starts at some point away from the origin, but it's not moving. The object stays at that position for all of time. Okay, the position isn't increasing or decreasing, it's not going away from or towards the origin, it's got no slope. So the object isn't moving, it's staying at that same position, again, because it has a 0 slope. So that's what that's telling us. The object isn't moving because of its 0 slope. So let's take a look at a more complex position versus time graph. We are only going to be recognizing the motion from these graphs, not actually making the graphs. So again, for position versus time, position on the y-axis, we measure in meters, always in physics, and time is on the x-axis, which we measure in seconds. Okay, so let's say I have a position versus time graph that looks something like this. And you'll notice that I've got a couple of those relationships all put together. I've got my positive linear, my no relationship, and my negative linear relationship all in there. So we're going to break down, what does this actually look like? What is this graph telling us? Let's say that this is a position versus time graph for a person that's walking. That's a really easy context for us. Okay, so first things first, we take a look at where does the object start when time is 0? Well, it's starting at the origin. Which, if you remember from my dinosaur video, I made that tree the origin. I made that my reference point, and my object, which was me in the T-Rex costume, started at the origin. So it's the same thing here. The object is starting at the origin, okay, which was that tree. So let me move that, make it a little smaller, okay? So our object is starting at the origin, and what is it doing after that? So we notice that as time increases, our position is increasing as well at the start. We've got a positive linear relationship, which, if you remember, that's telling us that our person is walking away from the origin at a constant positive rate. So they're moving away from the origin. So again, just like I did in the T-Rex costume, I was walking away from that tree, walking away from the origin. That's what that means. Okay? So again, we've got a positive slope there, positive linear relationship. It's walking forwards away from the origin. But then we notice we've got a segment there, that pink segment has 0 slope. So as time is increasing, the position is not changing. The position stays at the same position. The person isn't moving. The person stops moving, and they stop moving for a short amount of time. We'll just say that that's a couple seconds. So the person stops for a few seconds. So just like I did in the video, I was standing there for a few seconds, and then I continued moving. Okay, so I'm just going to move that out of the way as we continue with this graph. So we had a person walking away from the origin, stopping for a few seconds, and then what do we notice? Well, that we've got a negative linear relationship here, and that's telling us that the person is then walking back towards the origin. Okay, they're walking back where they came from. They're walking back towards that origin line in our graph, right, where position is equal to 0. So they started at the origin and they end at the origin. So they're walking back towards where they started. Okay, so if, again, for my T-Rex example, I started at the origin, which was the tree, and then I walked back towards the origin, which was the tree. Okay, so that's kind of that context there. The last kind of thing we want to talk about is what these slopes mean. These slopes are really important on a position versus time graph. So you'll notice that at the beginning we had that positive slope, and then at the end we had a negative slope, but which one of those two is steeper? This is really important here. It's actually the negative slope, okay? So if you notice, that's a really high slope, it's really steep. And if you notice, we only had a slope when the person was walking. when the person was moving. So when we had that positive slope, the person was walking away at a constant positive rate. So they had a slope and they were walking. And then when we had that negative slope, they were walking back towards the origin at a negative rate. So what is the slope telling us? This is a huge idea for us in physics. The slope is actually telling us when somebody is walking, because if we don't have a slope, the person isn't walking. Let that sink in for a second. That means that the slope is telling us the velocity of the person, right? When we had a positive slope, the person was walking forwards, in the forwards direction, away from the origin. When the person had a negative slope, they were walking backwards in the negative direction, back towards the origin. And when the person didn't have a slope, the person wasn't moving. So that means the slope tells us the velocity of the person, and the steeper the slope, the higher that slope is, the steeper it is, that means the higher the velocity we have. So if we've got a really, really steep slope, that means that person is moving really quickly. They've got a high velocity. So that means our negative slope of our graph, it was steeper, which means that person had a really high velocity as they were moving back towards the origin in comparison to when they were walking away from the origin. There, that's not as steep of a slope. Okay, so again, the steeper the slope means the higher the velocity, but the, I guess, lazier the slope, or the lower the slope, the lower the velocity, the slower the velocity. So this is kind of a complex idea. We're really going to keep unpacking these ideas of position versus time graphs. What are they telling us? What information can we gain from them? So this was a really fast and furious overview, but we're going to be spending a lot of time over the next few days continuing with this idea.